Hi, I'm Archit. In this presentation, I'll be giving a brief introduction to quantum computing, and I'll discuss how quantum computers can accelerate medical research and help us provide better healthcare. In the first half, I'll explain the fundamentals of quantum computing, and then the second half will mostly focus on their application. So let's get started. As you may know, there are many different types of computers, and advancements in the field of quantum computing will not directly have any impact on the user end. Even 50 years from now, it's very unlikely that quantum computers will replace our digital computers. The reason being that quantum computers are simply not good at things such as logic, pattern recognition, and image processing. They will, however, make supercomputers or analog computers virtually useless. So, what exactly is quantum computing, and what are quantum computers? Well, simply put, these are computers that harness the phenomena of quantum mechanics, and quantum mechanics itself deals with the behavior of matter and light on atomic and subatomic scales. And as you may know, at the very fundamental level of a supercomputer, there are bits, zeros and ones, which are the smallest units of data. A bit can exist as either a 0 or a 1. However, in a quantum computer, there are no bits, we have qubits, and a qubit can exist as a 0 and a 1 at the same time. Unless a qubit is observed, it exists as a 0 and a 1 in space-time. This unique property is known as superposition. We can assign probabilities to each state using the superposition equations, and this characteristic is at the core of what makes these computers more advanced, and I'm using the term advanced loosely here than supercomputers. Imagine that you had a primitive 500 qubit quantum computer that could store 2 to the power of 500 values in parallel. You'd never be able to describe this entanglement with a normal supercomputer, because that's more than the number of atoms in the universe. And a quantum computer can actually do this, and this is quite mind-blowing. And there are 3 key characteristics which differentiate quantum computers from supercomputers and enable them to have a high throughput. The first property is, of course, quantum superposition of the qubits. The second property is quantum entanglement. This is when 2 qubits that share spatial proximity interact in such a way that the quantum state of one qubit cannot be described independently of the state of the other. The last key feature is quantum annealing. So let's say you're trying to effectively solve an optimization problem. Let's say you're trying to create an investment portfolio that minimizes risk and maximizes return. How would you go about doing it? Well, quantum physics can help solve these sorts of problems because you can frame them as energy minimization problems. A fundamental rule in physics is that everything tends to seek a minimum energy state. Objects slide down hills and hot things cool down over time. This behavior is also true in the world of quantum physics. And quantum annealing simply uses quantum physics to find low energy states of a problem. Lastly, let's talk about some of the use cases of quantum computers. Quantum computers are insanely good at optimization problems, thanks to, of course, quantum annealing. They're very good at solving differential equations, which can help model the behavior of complex systems. And later on, we will look at how this can help with clinical trials and drug development. These computers can also solve complex linear algebra problems, and they can be used in machine learning. Lastly, things like conventional cryptography are based on prime factors. It's computationally expensive and long. We're talking millions of years for supercomputers to do this. Quantum computers, on the other hand, can calculate these in a matter of minutes. Now that we've had a look at the basics of quantum computing, let's look at how their implementation in medical provision and research has the potential to quite possibly revolutionize medicine for the good. In silico trials means that no humans, no animals, not even a single cell is required for testing a particular therapy, treatment option, or drug, yet its impact can be perfectly charted. Completely simulated clinical trials are just not feasible with the current technology and understanding of biology yet, but that development would be expected to have major benefits over current in vivo trials. Quantum computing could greatly advance the building of, quote, virtual humans in complete simulations such as the HumMod, which features thousands of equations and variables. You can see some of them listed at the bottom of the screen. It would even open the door to live clinical trials with as many virtual patients as possible and with components of the likings of the testers. It would not only massively shorten the time necessary for such trials, but also their quality and completeness. A few years ago, in a TED Talk, Shahini Ghosh mentioned the use of quantum uncertainty for encryption as one of the most probable applications of quantum computing. She believes it could be used for creating private keys for encrypting messages sent from one location to another, so that the hackers could not copy the key perfectly due to quantum uncertainty. The hackers would have to literally break the laws of quantum physics to hack such keys. Now, imagine that level of security with regards to sensitive medical information, electronic health records, genetic and genomic data, or any other private information that the healthcare system, the NHS, generates about our bodies. We've long surpassed the era when the accumulated knowledge of medical professionals could reside in one professor's head. It's just too much. If you go on PubMed, there are 31 million research papers, and if a single doctor could only read 3 to 4 studies per week, they could not finish it in a lifetime, and meanwhile millions of new studies would come out. That has already been a problem for a while. Thus, IBM created a supercomputer and its algorithm IBM Watson to sift through these studies. But quantum computing would take that to a whole new level. What if such computers could offer perfect decision support for doctors? They could skim through all the studies at once, they could find correlations and causations that the human eye would never find, and it might just stumble upon diagnoses or treatment options that the human doctor could have never figured out by themselves. The design and analysis of molecules for drug development is a challenging problem today, and that's because exactly describing and calculating all of the quantum properties of all the atoms in the molecule is a computationally difficult task, even for our supercomputers. And in a quantum computer, to double the throughput, you don't need to double the number of qubits, you just need one extra bit. In the computer-aided drug discovery design process, CADD, increasing the accuracy of molecular simulations incurs a punishing increase in computational cost. Quantum computing could transform the way we think about the simulation of molecules, atoms, and subatomic particles. Firstly, it could help overcome the scaling limitations of classical computational methods and allow for numerically exact solutions to the Schrödinger equation for larger and more complex molecular systems. Quantum computing will be applicable to many of the workflows in CADD. The present and near-term applications focus on molecular similarity, protein structure prediction, and protein design, but quantum computing will also be relevant to quantum chemistry and molecule docking. Most of the near-term applications are concerned with reframing problems in drug discovery as energy minimization problems and using a quantum device to solve these bottlenecks. Running searches on quantum computers could unfold looking through all possible molecules with unimaginable speed, drug target tests conducted in every potential cell model, or in silico human tissues and networks in the shortest amount of time possible. This would open the gates to find the antidote to diseases we never dreamt about before. Alzheimer's, various types of cancer. The possibilities seem to become endless. There are so many applications of quantum computing in medicine, sequencing and analysing DNA and whatnot. Who knows what application we will discover next? However, we must progress carefully and responsibly as we build our quantum future. And for me, personally, I don't see quantum physics as a tool to just build quantum computers. I see quantum computers as a way for us to probe the mysteries of nature and reveal more about this hidden world outside of our experiences. How amazing that we humans, with our relatively limited access to the universe, can still see far beyond our horizons just using our imagination. And the universe rewards us by showing us how incredibly interesting and surprising it is. The future is fundamentally uncertain, and that to me is certainly exciting.